This is the next video in the chapter on electronic structure and periodic properties. We were just talking about how light acted like a wave mostly, but some of the properties of light aren't like waves. Some of the properties are like particles. Specifically, light is quantized. So let's talk about what properties quantized light has. So particle properties of light. If we're talking about light as a series of particles, put that in quotations, we have a special name for those. We call them photons. Photons are these packets of energy that behave like particles. And these photons have specific allowed energy values because they're quantized, just like shoe sizes. And it's important for us to know what sorts of allowed energy values there are. So Einstein gave us this formula to help describe the energy of a photon. That is E equals H times nu. So what are these letters? So E is the energy of a photon, a particle-like packet of light, and that's measured in joules with a capital J. On the end here, nu, that's frequency. We talked about that in the last video. And frequency is measured in 1/seconds or hertz. And then this H in the middle, this is Planck's constant, named after Max Planck, or Max Planck technically. And Max Planck was the one who had the first idea that light could be quantized. And the Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. So we have joules times seconds multiplied by 1/seconds, and that gives us joules. So we now can say light acts like a wave sometimes. And when it does, we have a formula to help describe it. What's nu? C over lambda. And sometimes light also acts like a particle, which is basically the understatement of the century, but let's just go with it. And when light acts like a particle, we can describe it with the formula energy equals Planck's constant times nu. So which is it? Is it a light? Is light a wave? Or is it a particle? And the short answer is it's both. Physics had to be rewritten and redesigned to incorporate the fact that light was both a wave and a particle. And the revolution was called wave-particle duality. And understanding wave-particle duality has permitted much of our current technology to exist. So if light is both a wave and a particle, then we should be able to use both of these formulas to describe it. So we can substitute this formula into the other one, substitute in for nu, and that gives us E equals Planck's constant times this formula for nu, C over lambda. So E equals H times C over lambda. And that's our most useful way of calculating the energy of light. We can calculate it based on the frequency or based on the wavelength. So let's make sure we're familiar with how to use that. We'll do a couple of examples that I have pre-written here. Take a moment and pause the video if you need to write these down. So Well, to continue our talk about GPS, like in the last video, a GPS signal photon has this frequency, same as before. Find the energy of one single photon. So if we need to convert between something like wavelength or frequency and energy, we're going to use one of these important formulas in our list here. So frequency is going to be the nu, so we can use E equals h times nu to find our energy. So h is Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. And then our frequency, we did the conversion to hertz the last time we used this number. So it was 1.575 and then times 10 to the 9th to convert that into hertz or inverse seconds. Okay, and our inverse seconds cancels with our seconds. It leaves us with joules. And if you type this into your calculator, you should end up with 1.044 times 10 to the negative 24th. And that's how many joules of energy are in one single photon. Specifically, a photon of 1.575 hertz GPS signal. Remember, as every different frequency of photon has a different energy. Now for a trickier one. So you have a GPS and it's emitting these frequency photons. And let's say the GPS emits a burst of 5.0 times 10 to the 17th photons. What is the total energy of all the photons in the burst? So each of the photons has this much energy, and we have this many photons. So the total energy is going to be a sum of the energy of each of the photons involved. I'm going to start with the number of photons, 5 times 10 to the 17th photons. And I'm going to use this answer from the previous one as a conversion factor because it has both the unit joules and the unit photon in it. So this conversion factor says 1 photon of this particular frequency has an energy of 1.044 times 10 to the negative 24th joules. And if I multiply that by the number of photons, photon will cancel and we'll be left with joules. And if we type that into our calculator, we should get 5.2 times 10 to the negative 7th joules in that burst of photons. So all this to say that photon energy is additive. If you have one photon, it has a particular energy. If you have multiple of those photons, the total energy is the sum of all of them. So now we know that light can behave both as a wave and as a particle, and somehow it can be described as both of those at the same time using the formula E equals h times c over lambda. And so in the next video, we'll use this information to adapt our current view of what an atom looks like to account for this new information.